Imagine standing on a vast plain, looking out at a city. You see the glittering lights, the buildings, the movement. But what if I told you that the true substance, the overwhelming majority of the city's mass, was completely invisible? That the lights and buildings you perceive are merely the decorative frosting on an immense unseen cake? This is the reality of our universe. For decades, astronomers have observed galaxies, those islands of stars, gas, and dust, spinning and interacting in ways that defy the visible matter alone. They move too fast. They clump together too readily. The gravity holding them together, influencing their orbits, seems to be far, far stronger than the sum of all the stars, nebulae, and planets we can detect. Something colossal, something pervasive, is missing from our cosmic inventory. We call it dark matter. But it's not just a sprinkling. It forms the scaffolding upon which entire galaxies are built. We're talking about invisible giants, cosmic behemoths, that dwarf the luminous galaxies they host. These are the dark matter halos, the universe's unseen architects, and their story is one of cosmic destiny. Our journey into the realm of dark matter halos begins not with a telescope, but with a deep dive into the laws of gravity and motion. In the 1930s, Swiss astronomer Fritz Zwicky, studying the Coma cluster of galaxies, noticed something profoundly odd. He calculated the mass of the cluster based on the visible light emitted by its galaxies. Then he measured the velocities of those galaxies. According to Newtonian physics, the galaxies were moving far too quickly to be gravitationally bound by the visible mass. They should have flown apart, like a ball thrown too hard. Zwicky posited the existence of dunkle Materie, dark matter, to provide the necessary gravitational glue. His calculations suggested that the cluster contained hundreds of times more mass than could be accounted for by its luminous galaxies. His ideas were largely dismissed at the time, considered an anomaly. It wasn't until the 1970s, with the meticulous work of Vera Rubin and Kent Ford, that the evidence became impossible to ignore. They studied the rotation curves of individual galaxies, plotting the speed of stars and gas clouds at different distances from the galactic center. What they found was revolutionary. Stars far from the center were orbiting just as fast, if not faster, than those closer in. This suggested a massive, unseen halo of matter, extending far beyond the visible disk, providing the extra gravity to keep these outer stars tethered. So, what is this elusive dark matter? The short answer is, we don't precisely know, but we know what it isn't. It's not ordinary baryonic matter, the stuff of stars, planets, and us. It doesn't interact with light, hence dark. It doesn't absorb, emit, or reflect electromagnetic radiation. This makes it incredibly difficult to detect directly. We infer its presence solely through its gravitational effects on visible matter. The leading candidates for dark matter particles are weakly interacting massive particles, or WIMPs. These hypothetical particles would have been created in abundance in the early universe, interacting only through gravity and the weak nuclear force. They would be slow-moving, making them cold dark matter, which fits our models of large-scale structure formation. Other theories propose lighter, faster particles, warm dark matter, or even modifications to gravity itself. Experiments deep underground, shielded from cosmic rays, are attempting to directly detect the faint interactions of WIMPs as they pass through Earth. Particle accelerators are trying to create them, but so far, definitive proof remains elusive, leaving dark matter one of the most profound mysteries in modern physics. Dark matter isn't just a component of galaxies, it's their cradle. The prevailing cosmological model, lambda CDM, suggests that the universe began with tiny quantum fluctuations. In the aftermath of the Big Bang, these fluctuations were amplified, seeding regions with slightly higher densities of matter, including dark matter. These denser regions began to attract more dark matter, growing into vast gravitationally bound structures. Over cosmic time, these halos of dark matter acted as gravitational wells. Ordinary baryonic matter, initially dispersed throughout the universe, was drawn into these wells. As gas fell into the dark matter halos, it cooled, condensed, and eventually ignited star formation. The first galaxies are thought to have formed within these primordial dark matter halos. Thus, the luminous galaxies we see today, the Milky Way, Andromeda, and all the others, are merely the visible tips of an enormous, unseen iceberg of dark matter. The size and mass of these halos are staggering, often extending hundreds of thousands, even millions of light years. The sheer scale of these dark matter halos is difficult to comprehend. A typical Milky Way-sized galaxy resides within a dark matter halo estimated to be roughly 10 times larger in diameter than the visible galaxy itself. The mass contained within this halo is estimated to be around 10 times the mass of all the stars, gas, and dust combined. For the Andromeda galaxy, our nearest large neighbor, its dark matter halo is even more massive, extending perhaps 1 million light-years into intergalactic space. These halos are not uniform spheres. They are complex, lumpy structures, often containing substructures, smaller dark matter clumps that have merged or are in the process of merging with the larger halo. These substructures can host dwarf galaxies, or even be entirely devoid of visible matter, detectable only by their gravitational influence. The hierarchy of structure formation, where small clumps merge to form larger ones, is a key prediction of the cold dark matter model, and is strongly supported by observations of galactic distribution and satellite galaxies orbiting larger systems. One of the most powerful tools we have for probing these invisible halos is gravitational lensing. Einstein's theory of general relativity predicts that massive objects warp space-time, causing light from background objects to bend as it passes by. This effect is known as gravitational lensing. Dark matter halos, being incredibly massive, exert a significant gravitational pull that can distort and magnify the light from distant galaxies. By studying how the images of these background galaxies are distorted, stretched, sheared, or even appearing as multiple images, astronomers can map the distribution and infer the mass of the intervening dark matter. The bullet cluster, a collision between two galaxy clusters, provides a spectacular example. Observations show that the hot, luminous gas, baryonic matter, was slowed by the collision, while the majority of the mass, detected through lensing, passed right through, indicating that it is composed of non-interacting dark matter that formed the cluster's underlying structure. This separation of visible gas and inferred dark matter is a smoking gun for dark matter. Cosmological simulations are essential for understanding how these dark matter halos form and evolve. These incredibly complex computer models start with the conditions of the early universe, as predicted by the Big Bang theory, and then simulate billions of years of cosmic evolution under the influence of gravity and the lambda CDM model. They show dark matter coalescing into vast filaments and nodes, forming the so-called cosmic web. Galaxies and galaxy clusters then form at the intersections of these filaments, within the densest regions of dark matter concentration, the halos. These simulations can reproduce many observed features of the universe, such as the distribution of galaxies on large scales and the abundance of different types of galaxies. By comparing simulation results with observational data, cosmologists can refine their understanding of dark matter properties and test different theoretical models. Projects like the Millennium simulation and the illustrious TNG simulations have created detailed maps of the universe's large-scale structure, revealing the intricate interplay between dark matter and galaxy formation over cosmic epochs. The distribution and properties of dark matter halos have profound implications for our understanding of galaxy formation and evolution. The hierarchical model, where smaller halos merge to form larger ones, explains why larger galaxies often reside in more massive dark matter halos, and why larger structures like galaxy clusters contain the most dark matter. The number and distribution of satellite galaxies orbiting larger galaxies, like the Milky Way's own retinue of dwarf galaxies, are also dictated by the substructure within the main dark matter halo. Furthermore, the environment within a dark matter halo influences the evolution of the galaxies it hosts. Mergers between galaxies, driven by the gravitational pull of their halos, can trigger intense bursts of star formation or fuel the growth of supermassive black holes at galactic centers. The properties of the halo itself, such as its shape and density profile, can also affect the morphology and dynamics of the galaxy within it. The quest to understand dark matter halos is far from over. While gravitational lensing and large-scale structure observations provide strong evidence for their existence and distribution, the fundamental nature of dark matter remains one of the greatest unsolved puzzles in science. Ongoing and future experiments, from underground detectors searching for WIMP interactions to advanced telescopes like the Vera-C, Rubin Observatory, and the Nancy Grace Roman Space Telescope, aim to map dark matter distributions with unprecedented precision and potentially shed light on its composition. Understanding dark matter halos is not just about identifying an invisible substance. It's about comprehending the fundamental architecture of the cosmos. These unseen structures are the bedrock upon which galaxies are built, the gravitational architects that dictate the fate of cosmic structures, and a constant, tantalizing reminder of how much more there is to discover in the vast, dark expanse of the universe.